Let's continue with the back page of the optimization worksheet number 2. Okay, so this is number 3 here. A cylindrical can is to hold 20 pi cubic meters. The material for the top and bottom costs $10 per square meters, and the material for the side costs $8 per square meters. Find the radius and height of the most economical can. So basically, the can that has that's going to cost the least. So so we have a cylindrical can here. Here's formulas that we need. So surface area is going to be area of the two bases, top and bottom, circular bases, and also the surface area of the sides, the circular side that's connecting the two bases. And then the volume formula for a cylinder is pi r squared h. Okay, so we're trying to find the most cost-efficient can, so that's going to be related with the surface area. So let's think about what the cost formula looks like. So the cost formula is going to be $10 for each of the bases and $8 for the sides, the material for the sides, so $8 per square meters. So if we combine that together, we get 10 pi r squared plus 10 pi r squared will be 20 pi r squared plus 16 pi r h. Okay, so again, $10 for every for each of the area involved with the base, another $10 for the other base, and $8 for the material involved with the sides, creating the can. All right, so we simplify this. We have our cost equation. But now we want to find the derivative, but there's one variable that's that we have to deal with, and that's the h, right? So remember, pi is just a coefficient. We don't have to worry about that, but we can't find the derivative yet if we have r squared and h. So we have to find a way to reduce our equation down to one variable on the right side. So it looks like the one that will be the easiest to replace will be h. So to deal with the height, we can use the other equation, which is available to us, which is the volume equation. Okay, now we know that the volume of the can is to be 20 pi cubic meters. So if I replace volume with 20 pi, I can solve for h, divide both sides by by pi r squared. The pi's cancel out. We get 20 over r squared is equal to h. So then h gets replaced with 20 over r squared. Simplify, cancel out, and we have 20 pi r squared plus 20 times 16 is 320 pi r to the negative 1. We now have our equation that's set up and ready for us to find the derivative using power rule. So then to find c prime, or the derivative equation for the cost, we go through power rule. So bring down the 2. 2 times 20 is 40 pi r. Negative 1 times 320 is negative 320 pi r to the negative 2. Going through power rule, subtract 1 from the exponent. Once we have our derivative, we can simplify, clean this up, set it equal to 0, set our derivative equal to 0 to find our critical point. I'm going to move the 40 pi r to the left side, divide both sides by negative 1, do cross product. We get to 40 pi r cubed equals 320 pi. Bring everything over to one side here. I can factor out the 40 pi. And then solve for r. R cubed is 8, so r must be equal to 2 meters. Okay, so if the radius is 2, then the height, right, if I replace 2 in for r squared, then 20 over 4 is going to be 5, so that will allow us to find our height of the most economical can is 5 meters. All right, number 4, there are 50 apple trees in the orchard. Each tree produces 800 apples. For each additional tree planted, the output per tree drops by 10 apples. How many trees should be added to the existing orchard in order to maximize the total output of trees? All right, so let's think about this equation here. So the total production is going to be the number of trees multiplied by the apple output per tree. Okay, so that means each tree that we add, we're going to lose an output of 10 trees or 10 apples per tree. So we're trying to find how many trees can we add that will optimize the total output of trees. So So this is our equation. We start off with 50 trees, and we want to figure out how many can we add, but then each time we add, we have to make sure that we adjust the output per tree. All right, once we have our equation, then we can distribute, expand, and combine like terms. There's nothing to combine here, so we can, once we expand it, we can go through power rule. 40,000, going through power rule to find the derivative, because we're trying to find the derivative of derivative equation. So 40,000 goes to 0, 300x goes to 300, negative 10x squared becomes negative 2x. We set this equal to 0 to find our critical point. Factor out the 20 here, and then we solve for x, so x equals 15. So if x equals to 15, that means we can add 15 trees to the garden here. So 15 plus the existing of 50 will mean 65 trees should be added.